Ladies and gentlemen, welcome to our MLAB demonstration. With us today we have Gary Knott, who's going to take us through a couple of simple MLAB functions to just sort of give the flavor of how MLAB works, and then afterwards he's going to talk us through chemical kinetics and how to model second order binding in MLAB. Take it away, Gary.
Okay, here we go. So first thing we're going to do is run the MLAB program. So we come up to the icon, click, click. Here's MLAB. And we will now go to top level MLAB, even though you should go look at the demonstration do files when you're running MLAB just to see what it can do. And here's the MLAB text window. It is where you type MLAB commands. MLAB is an interpreter, and it has a language, a mathematical language, which we use to control what you're going to do. So what we're going to do is start out by just showing you that you can do simple definition of functions and graphs and so on in MLAB. So we'll just say function, FCT, f of x comma y is equal to, let us say, x times y. And there's a function, and if I say f, I verify that it's defined in MLAB. And if I say f prime x, there's the derivative of f with respect to x, which is kind of cute. And now we say, for example, function g of a and b and c is equal to f of a comma b times c, let's say. And that's a function which is using f as an auxiliary function. And it's also computable, of course. If we say g of 1 comma 2 comma 3, we should get what? 1 times 2 is f of 1 and 2, and times 3 should get 6, and we do.
Very good.
Okay, next step is to look at a somewhat more substantial function. Let's look at this one. Function of, let's use f again, of x, just f of x, is equal to cosine of b times x times the exponential of minus k times x. Okay, that function is a decaying oscillation. Why is it a decaying oscillation? Because the cosine is an oscillation and the exponential of a negative exponent decays away. And so we should be able to see that, and we will when we draw a graph of it. And notice we've redefined f. F is now a new function. But this won't work as it stands. Let's try to compute f of 2. And we get an error message. Why? Because the constants b and k in this function are not defined. They are parameters that have been given no definition. So we hit escape to continue typing commands. And what we need to do is set b equal to, let's say, 1. And we can put two things on a line with a semicolon. And we'll say k is equal to 0.2. So there's a specific set of values for the parameters b and k. And now we can compute f. F of 2 is equal to, well, there it is. And let's see what this function is. So we'll draw a graph of it. Draw the points that you get in the plane, that's two-dimensional points, of the function f. You make a graph of x for x running between 0 through, let's say, 4 in 120 steps. That means 120 points will be plotted. And we'll look at the picture, view, and there's our oscillation.
Very nice.
But unfortunately, this didn't go very far. This oscillation is kind of long and wide. So let us, and in fact, I think what we should do just to make it fit the recording screen is move it over a little bit. There it is. And now we should click here, and we should draw a little more. So
can you extend the graph?
We will exactly do that. So now what we're going to do is just say draw the points of f. Now we could go 0 to 4 again, 0 to 8, whatever we want, but we've already done 0 to 4, so let's just do 4 through 20. again in this time 220 points, more points, and just to show that it's a different curve, we'll say line type. We could say line, not line E, line, or we could just say LT, it doesn't matter. Line type dashed, a dashed line. So do that, and there is our continuation graph, and you can see that it is indeed a damped oscillation. It's a cosine oscillation that's going down and converging to zero.
Very good. So this actually represents two graphs, right, Gary?
Yeah, that's
two graphs.
Two curves in the same plot.
Very nice.
Right.
Very nice.
Very
Hey,
good.
Gary, when you redefined f, you have a function g that's dependent on f. What
Yep.
happened to g?
Well, let's find out. G is still around. It doesn't know any difference, but the f is now changed. So if you say g of 1, 2, 3, oops, that was 1.2.3, 1, 2, 3, you get a problem. And why do you get a problem? Because f has got one argument now.
Yes.
F. It's only f of x. So f of AB no longer exists, and it's got an incorrect number of arguments supplied.
So therefore g is invalid, right?
G is definitely invalid.
Very good.
And there's no way we could fix it except to say function g of a comma b comma c is equal to, for example, a times f of b. And notice that's a different b than the parameter b. That's an argument b times c. Now that function is perfectly well defined if we say f of 1, 2, 3. Well, we still get a bug. Why do we get a bug there? Let's find out. Escape. Okay, we have f. F is a function of x. It's two parameters. And g is a function of a times, oh, well, guess what? That should have worked, as I think. So let's find out again. Did I mistype that? G of 1, 2, 3. Close. Okay. Oh, can you see what I did wrong?
No, I don't see it, but...
Well, scroll back.
Okay.
Right there. Can you see that I said compute f of 1, 2, 3?
You meant to say g, of course.
I meant to say g of 1, 2,
there
3.
you go.
So, of course, MLAB will not do what it is not supposed to be able to do.
Very good.
Okay, so g of 1, 2, 3, on the other hand, is a perfectly good value.
Very good.
All right, so we've been fooling with elementary functions here. Now let's use functions for what MLAB really wants to use them for, which is to define mathematical models that describe real problems in science or economics or whatever domain you can imagine applying a mathematical modeling tool to.